All right, get ready, everyone, because today we're going to do a deep dive into the world of coordination compounds.
Oh, cool.
These aren't like your typical chemical structures. We're talking about metal atoms,
Right.
often transition metals,
Yeah.
and they're surrounded by molecules or ions,
Uh-huh.
and these are called ligands. It's
Oh.
kind of like, a central hub with
Mm-hmm.
connecting spokes,
Yeah.
and they just create some really unique and really fascinating chemistry.
What I think is fascinating is how essential these compounds are.
Hmm.
I mean, you see them everywhere,
Yeah.
from biological systems like the hemoglobin in our blood
Oh, wow.
to industrial processes like catalysis.
Right.
Coordination compounds really are everywhere.
Yeah, exactly. And what makes them even cooler is that, like,
Yeah.
seemingly minor changes in a compound structure
Right.
can lead to some pretty dramatic shifts in its properties.
Totally.
And we're talking about things like color changes,
Yeah.
changes in magnetic behavior, even differences in biological activity.
This is where the concept of chelates comes in.
Okay.
So these are special types of coordination compounds where the ligands, instead of just attaching at one point, actually form a ring around the metal atom.
Interesting.
Imagine like tiny claws grabbing onto the metal center.
Okay, I can picture that.
Yeah.
But before we get too deep into the chelate clause,
Okay.
let's make sure that everyone listening is comfortable with some of the basics.
Right.
So what are some, I guess, key terms we need to understand when we're talking about these coordination compounds?
Well, the first term is complex,
Yeah.
which is simply a central metal atom or ion
Right.
surrounded by its ligands.
Okay.
And the number of ligands directly attached to that metal.
Yeah.
That's called the coordination number.
So if the metal has, let's say, a coordination number of 6,
Mm-hmm.
does that mean that it always has 6 ligands attached?
That is a great question.
Yeah.
Yes, the coordination number.
Okay.
It tells us how many ligands are directly bonded to the metal ion in what's called the inner sphere.
Okay.
Sometimes you might have other ions or molecules
Right.
that are kind of loosely associated with the complex
Yeah.
in what we call the outer sphere,
Uh-huh.
but they're not directly bonded to that metal center.
Okay. So it's like the inner circle versus the outer circle of
Yeah.
friends.
That's a good way to put it.
Okay. And what about these ligands?
Yeah.
What kinds of molecules can act as ligands?
Oh, there's a huge variety.
Okay.
Everything from simple molecules like water
Okay.
to more complex organic molecules.
Wait, water?
Yeah.
Like the stuff we drink?
Yep.
Wow.
Even plain old water can act as a ligand.
Interesting.
And what determines whether a molecule can be a ligand is the presence of what we call a donor atom.
Okay.
And this is a specific atom on the ligand
Mm-hmm.
that shares its electrons with the metal,
Ah.
forming a bond.
So if I'm understanding this correctly,
Yeah.
the donor atom is like the generous friend
Okay.
offering to share their snacks.
Uh-huh.
And the electrons of the snacks
Okay.
being shared.
You got it.
All right, cool. I'm feeling pretty good about the basics so far.
Yeah.
But I've noticed that
Mm.
coordination compounds often have some pretty intimidating names.
Oh, yeah.
How do chemists come up with those tongue twisters?
So there's actually a very systematic method for
Yeah.
naming these compounds.
Right.
But I'll admit, the names can get quite long and complex,
Yeah.
especially when you have a lot of different ligands
Mhm.
or a really complicated structure.
So it's like a code, but for molecules.
Exactly.
Right.
Each part of the name tells you something specific
Right.
about the compound's composition
Mm.
and structure.
Okay.
For example, the ligands are listed in alphabetical order, and prefixes like di, tri, or tetra are used to indicate how many of each type are present.
Okay, so there's a method to the madness.
Yes.
But can you give us an example of like a particularly wild name just to see how this naming system works in action?
How about this one? Pentamine aquacobalt 3 chloride.
Whoa, that's a mouthful.
Yeah,
Can we try to break that down?
absolutely.
Okay.
So that name tells us we have a cobalt ion with a +3 charge.
Okay.
It's surrounded by 6 ligands,
Mm-hmm.
5 ammonia molecules, which is where the pentamine comes from,
Gotcha.
and 1 water molecule, the aqua.
Okay.
And outside the coordination sphere, we have a chloride ion as the counterion.
Okay, I see how the pieces kind of fit together,
Yeah,
like a puzzle to describe the whole compound,
exactly.
like a molecular blueprint.
Yeah, that's a good way to think about it.
Cool. So we've talked about ligands, coordination numbers,
Mm-hmm.
and even how to decipher those crazy names.
Right.
But I'm guessing the arrangement of these ligands around the metal center also matters too, right?
You're absolutely right.
Okay.
So the geometry or spatial arrangement of a coordination compound is a key factor in determining its properties. It's like how rearranging furniture in a room
Okay.
can totally change its look and feel.
Right.
Different geometries can lead to differences in color, stability, reactivity,
Wow.
and even biological activity.
Okay. So what are some common geometries that we might encounter in the world of coordination compounds?
Well, one of the most common is octahedral geometry,
Okay.
where you have 6 ligands surrounding the metal atom.
Okay.
Picture the metal atom at the center of a cube with the ligands occupying each corner.
Okay.
This is seen a lot, especially in complexes of transition metals.
Gotcha. Okay, I can picture that. It's a very symmetrical arrangement.
Yes, very symmetrical.
What other shapes might we see?
Another common one is tetrahedral geometry,
Okay.
where 4 ligands are arranged around the metal.
Right.
Think of it like a pyramid
Okay.
with a triangular base
Mm-hmm.
and metal at the apex.
That makes sense.
Yeah,
So it's like the metal's at the peak of the pyramid.
exactly.
Okay, so we've got the cube-like octahedral and the pyramid-like tetrahedral.
Uh-huh.
Are there any other popular geometries?
Yeah, square planar geometry is also fairly common,
Okay.
especially for certain metal ions.
Okay.
In this case, 4 ligands are arranged around the metal
Mm-hmm.
in a flat square.
So a square. Okay, so we've got 3 main geometries to keep in mind.
Right.
Octahedral, tetrahedral, and square planar.
Yes.
And the geometry influences how the compound behaves, right?
Exactly. It affects how the compound interacts with light, other molecules, and even magnetic fields.
Wow.
But it gets even more interesting because sometimes you can have the same set of atoms arranged in different ways.
Okay.
And that leads to what are called isomers.
Isomers.
Yeah.
Those are like the molecular twins with
Yeah.
different personalities, right?
That's a great way to put it.
Same atoms,
Yeah,
but arranged differently.
exactly.
And with that, I think we've laid a pretty solid foundation for understanding the basics of coordination compounds.
I think so too.
What do you think?
Yeah.
Ready to delve a little deeper?
Oh, I'm ready. Let's go.
Let's keep this deep dive going.
Let's talk about those chelate claws.
Okay.
They play a crucial role in how stable these coordination compounds are.
Okay.
Just like friendships, you know?
Mm-hmm.
Some compounds are more tightly bound than others.
Right.
Yeah.
So how do chemists measure how close that bond is between the metal and its ligands?
Yeah.
Is there a popularity contest going on at the molecular level?
You could say that.
Okay.
We use something called formation constants,
Okay.
and a higher value means the complex is more likely to form and stay together.
So a high formation constant means
Yeah.
strong bond.
Yeah, strong bond.
Like those friends who are always together.
Exactly.
I bet those chelating ligands,
Yeah.
the ones with multiple points of attachment,
Yeah.
score pretty high.
Exactly.
Yeah.
That's the chelate effect in action.
Okay.
When a ligand can grab onto the metal
Well-
in multiple places. Right.
It forms a ring structure, and those rings tend to make the complex much more stable.
So I'm starting to see why you called them claws.
Yeah.
They really lock onto the metal.
They do.
But why are ring structures so good at this?
Right.
Like, what's the underlying reason why they stabilize a complex so well?
It all boils down to entropy.
Okay.
Now, entropy is a bit of a tricky concept,
Yeah.
but essentially it's a measure of disorder in a system.
Okay.
The more ways you can arrange things,
Uh-huh.
the higher the entropy.
So a messy room has higher entropy than
Yes.
the tidy one.
Precisely. Now, in a solution, you have all these metal ions and ligands moving around randomly.
Right.
When a chelating ligand comes along,
Yeah.
it brings multiple ligands together
Okay.
into a single organized ring,
Mhm.
and that reduces the overall disorder or entropy of the system.
Okay.
And nature loves to decrease entropy whenever possible.
So chelates are like the organizers of
Yeah.
the molecular world.
I like that. They tidy things up.
They do.
They bring order to chaos.
Yeah.
That's why they're so stable.
Exactly.
It's all about making things nice and tidy.
That's a fantastic way to think about it.
Cool.
And this isn't just a theoretical quirk.
Okay.
The chelate effect has huge implications in the real world.
Oh, tell me more. I'm always fascinated by how these tiny molecular interactions affect our lives.
Well, take medicine, for example.
Okay.
Chelating agents are used in chelation therapy to remove heavy metals from the body.
Wow.
These agents, they have a strong affinity for toxic metals,
Right.
like lead or mercury.
Yeah.
They bind to them,
Okay.
forming stable chalates,
Mm-hmm.
which can then be safely excreted from the body.
So chalates are like tiny superheroes.
They are.
Swooping in to detoxify us,
Yeah.
they grab onto those harmful metals
Yeah,
and escort them out.
that's right.
That's incredible.
And in environmental chemistry,
Yeah.
we use chelating agents to clean up contaminated soil and water.
Oh,
They can bind to pollutants like heavy metals
right.
and remove them from the environment.
So it's like a molecular cleanup crew.
Yeah.
They're restoring order
They are.
and balance to these polluted areas.
That's right.
Are there any other examples of chelates in action?
Absolutely. In fact, many essential molecules in biological systems rely on chelation.
Okay.
Chlorophyll,
Mm-hmm.
the pigment that makes plants green
Right.
and allows them to capture sunlight for photosynthesis,
Oh,
is
yeah.
a great example.
Okay.
It uses a special ring-shaped chelating ligand called a porphyrin to bind to a magnesium ion.
So chelates are essential for life as we know it.
They are.
From capturing sunlight to cleaning up pollution.
Yeah,
They're hard at work everywhere.
precisely. Now, there's another fascinating aspect of chelation that's worth mentioning.
Okay.
The macrocyclic effect.
Macrocyclic.
Macrocyclic.
It sounds big.
It is big.
Right.
Imagine a chelating ligand
Okay.
that's not just a ring,
Yeah.
but a large, elaborate ring structure.
Wow. That completely encloses the metal ion,
Okay.
like a crown.
Ooh, a molecular crown.
Yeah,
That sounds quite regal.
it does.
So how does this crown affect the stability of the complex?
Well, it basically amplifies the chelate effect.
Okay.
Macrocyclic complexes are even more stable
Right.
than their non-macrocyclic counterparts.
Yeah.
They have multiple points of attachment,
Right.
but the large ring structure provides extra stability because of its pre-organized shape. It just fits perfectly around the metal ion.
So it's like a custom-made suit
Yes.
for the metal.
Exactly.
Perfectly tailored for the ultimate instability.
A perfect analogy.
Go.
And this enhanced stability is incredibly important,
Okay.
especially in biological systems.
Mm-hmm.
Many essential molecules, like vitamin B12,
Right.
which is crucial for cell growth and development,
Yeah.
rely on macrocyclic ligands to bind metal ions and carry out their vital functions.
Wow. So these macrocycles are the VIP lounges
They are.
of the molecular world.
Yes, they offer the best in stability
Yeah,
and functionality.
That's right.
It's amazing how nature has evolved to use these structural features
Mhm.
to create such efficient and essential molecules.
Absolutely. Now, before we get completely swept away by the wonders of chelation,
Okay.
let's shift gears a bit
Right.
and revisit that intriguing world of isomerism.
Isomers.
Yeah.
Those molecular twins.
Yeah.
With different personalities.
That's right.
I remember we touched upon them earlier.
What's
What
that?
makes them so fascinating?
Well, remember, isomers have the same chemical formula, but different arrangements of atoms.
Right.
And these differences in arrangement can lead to some pretty significant differences in their properties.
Right.
We talked about geometric isomers, where the ligands are arranged differently around the metal center.
Okay.
But there's another type of isomerism that's equally important,
Okay.
structural isomerism.
So geometric isomers are like rearranging furniture in a room,
Yes.
while structural isomers are like using the same building blocks to create completely different structures.
A perfect analogy.
Okay.
In structural isomers,
Yeah.
the atoms are actually connected in different ways.
Oh.
For example, let's consider linkage isomerism.
All right.
This occurs when the same ligand can bind to the metal through different atoms.
Interesting.
It's like having multiple handshaking options.
Wait, so a ligand can choose which atom it wants to connect with.
It can.
What determines that choice?
Well, it depends on the ligand and the metal.
Okay.
But let's take thiocyanate ion, NCS, as
Sure.
an example.
Right.
This ion can bind to a metal either through the nitrogen atom
Okay.
or the sulfur atom,
Nitrogen.
creating completely different complexes with distinct properties.
So it's like the thiocyanate ligand is saying,
Okay.
do you want to shake my nitrogen hand
Yeah.
or my sulfur hand?
Exactly.
And depending on the choice, the whole relationship changes.
That's a fantastic way to visualize it.
Okay.
And the seemingly small difference in connectivity can have major consequences.
Okay.
For instance, one linkage isomer might be intensely colored,
Wow.
while the other is completely colorless.
So swapping a single atom in the connection can completely change the compound's properties.
It can.
It's amazing how subtle these structural changes can be,
Yeah.
yet have such dramatic effects.
It really highlights the power of molecular architecture,
Yeah.
and linkage isomerism is just one type of structural isomerism.
Okay.
We also have ionization isomerism,
Okay.
where a ligand and a cantarian switch places.
Cantarians, those are the ions that are hanging out
Yes.
outside the inner coordination sphere.
That's right.
Right.
Yeah.
Like the audience watching the show.
Yeah.
Not directly participating.
Exactly. So imagine a complex where a chloride ligand is inside the coordination sphere,
Okay.
and a bromide ion is outside, observing in an ionization isomer, the chloride and bromide would swap positions,
Okay.
with the chloride moving to the outer sphere and the bromide joining the inner coordination sphere.
So it's like someone from the audience
Yeah,
suddenly jumping on stage and joining the performance
exactly.
while one of the performers takes a seat in the audience.
That's right.
That's a major shift in dynamics.
It is.
Does this kind of swap happen often?
It can happen,
Okay.
and it can alter the compound's properties,
Okay.
particularly its solubility and reactivity.
So we've got linkage isomers,
Yeah.
where the ligand's connection changes,
Right.
and ionization isomers,
Right.
where the cast of characters switches roles.
Yeah.
Are there any other types of structural isomers?
There's also hydrate isomerism,
Okay.
where water molecules play a starring role.
Okay.
Remember, water can act as a ligand
Right.
in hydrate isomers.
Yeah.
The number of water molecules directly bound to the metal can vary,
Okay.
while the overall formula of the compound stays the same.
So it's like a hydration party,
Uh-huh.
but only some of the water molecules get to be in the inner circle.
That's-
Some are bound to the metal,
Yeah.
and others are just mingling in the outer sphere.
Exactly.
Does that happen often?
It can,
Okay.
especially for metal ions that have a strong affinity for water,
Got it.
and those subtle differences in hydration
Right.
can lead to distinct properties.
So we've got linkage, ionization,
Yeah.
and hydrate isomers.
Right.
They all involve rearranging the pieces
Uh-huh.
within a single complex.
That's right.
Are there any isomers where we're dealing with
Mhm.
multiple complexes interacting with each other?
You're thinking like a true chemist.
Okay.
Yes. There's a type called coordination isomers,
Okay.
which are a bit more complex.
Okay.
In these cases, you have two different complex ions present,
Mhm.
and the ligands are distributed differently between them.
So instead of just rearranging ligands
Mhm.
within a single complex, we're now looking at two separate complexes,
That's right.
each with their own set of ligands. And those ligands can be swapped between the complexes.
Exactly.
Okay.
It's like having two dance troupes,
Okay.
and the dancers can switch between the groups,
Gotcha.
creating completely different performances.
Wow. Coordination chemistry is full of surprises.
It is.
It seems like the possibilities for structural variation
Yeah.
are practically endless.
They are pretty much endless.
Right.
And the structural diversity is
Yeah.
what makes coordination chemistry so fascinating and
Right.
relevant to so many different fields.
Right.
But we've only scratched the surface of isomers.
Okay.
We still need to explore the mirror image world of stereoisomers,
Okay.
specifically enantiomers,
Okay.
and this fascinating phenomenon of chirality.
Chirality.
Yes.
That word always reminds me of my left and right hands.
Okay.
They're mirror images of each other.
Yeah.
But no matter how I twist and turn them, I
Mhm.
can't superimpose them perfectly.
That's an excellent analogy.
Okay.
And as we'll see, this concept of handedness at the molecular level,
Okay. Plays a crucial role in the properties and behavior of many coordination compounds,
interesting.
especially in biological systems.
Well, I'm definitely intrigued.
Good.
Let's step into the looking glass world of chiral molecules
Okay.
and uncover the secrets of their handedness.
Let's do it.
Lead the way. Okay, so let's dive into this looking glass world of chirality.
Yeah.
You mentioned earlier, like
Yeah.
left and right hands.
Mm-hmm.
How does that analogy actually apply to molecules?
Well, just like your hands,
Right.
some molecules exist as mirror images of each other.
Okay.
But you can't perfectly overlap them no matter how you rotate them.
Okay.
These mirror image molecules are called enantiomers.
So it's like trying to put a right-handed glove on your left hand.
Exactly.
It just doesn't fit quite right.
Yeah.
But why is this handedness such a big deal
Right.
in chemistry?
Yeah.
Does it really matter which hand a molecule has?
It can make a huge difference,
Okay.
especially in biological systems.
Right. Think about enzymes,
Okay.
those protein catalysts that speed up reactions in living organisms.
Enzymes, the worker bees of our cells.
Exactly.
Yeah.
Many enzymes are incredibly specific.
Okay.
They're designed to interact with only one enantiomer of a molecule.
Interesting.
It's a precise fit, like a lock and key.
So a left-handed molecule might not work with a right-handed enzyme,
That's right.
even if they have the same atoms and bonds.
Yeah, it's all about that 3D shape.
Right. It's all about the shape.
Yep.
Okay.
That's why chirality is so critical in drug design.
Mm,
Often, only one enantiomer of a drug will have the desired therapeutic effect,
right.
while the other might be inactive or even harmful.
Wow. So the wrong-handedness could mean a drug doesn't work or
Yeah,
even causes problems?
it could.
It's like the difference between a key that unlocks a door and one that jams the lock.
A great
And
analogy.
remember those octahedral complexes we talked about?
Yeah.
The ones with 6 ligands
Yeah.
around a central metal atom?
Right? Like a metal atom in the middle of a cube
Right.
with ligands at each corner.
Yes.
Well, if you have different types of ligands arranged in a specific way,
Uh-huh.
those complexes can be chiral too.
So it's like decorating that molecular cube with different colored ornaments.
Okay, yeah.
If you arrange them just right,
Yeah,
you can create a left-handed or a right-handed cube.
exactly.
Okay.
And just like with chiral drugs, these chiral coordination compounds can have different properties.
Interesting.
They might interact differently with light, other molecules, or even with biological systems.
This is really making me appreciate the complexity and subtlety of chemistry.
Yeah.
Even something as seemingly simple as the arrangement of atoms
Right.
around a metal can have such a profound impact
Yes.
on a compound's behavior.
It's a testament to the power of molecular architecture.
Yeah.
Small changes at the molecular level can ripple outwards,
Wow.
affecting everything from a compound's color to its biological activity.
Well, this has been an incredible journey into the world of coordination compounds.
It has.
I feel like I've gained a whole new understanding
Good.
of how these fascinating compounds work
Yeah.
and why they're so important
Right.
in so many areas of science.
It's been my pleasure to guide you through this deep dive.
Well, thank you.
And remember, we've only scratched the surface.
Right.
The world of chemistry is vast
Yeah.
and full of wonder.
It is.
Who knows what amazing discoveries await us
Right.
as we continue to explore the intricacies of the molecular world.
Well said. And to our listeners, thank you for joining us on this adventure into the fascinating realm of coordination compounds.
Yes, thank you.
We hope you've enjoyed learning about the central role these compounds play in everything from biological systems to medicine and environmental science.
Absolutely.
Keep exploring, keep learning, and keep those questions coming.
That's right.